improve the heat transfer rate, so you can have some fin. In order to improve the heat transfer further, you may put a fan. So there is convection, there is radiation. So you can also put on this fin, you can put black paint. When you put the black paint, what will happen? So this is the substrate. So let us say this is your chip, your electronic chip. Now we come to electronic cooling. Okay, if you are trying to attack this problem and your electrical engineer tells you it has to be at a temperature below 80 degrees or 85 degrees, then you design like this. In this case, the whole sink and the substrate and the chip they are all assumed to be at one temperature. If they are not at one temperature, then you have to solve for conduction in X direction, Y direction, Z direction. For this radiation, it's not so straightforward because the fins are seeing each other. So we use the view factor and so on. And if you are using some other phase change material and so on, or a jet impeachment cooling, so the calculation of each of these quantities, the calculation of this Q conduction, usually it may not be there in this case because otherwise it has to come to the left hand side. So the calculation of each of this is going to be very tough for you. Now, the challenge is now, so in electronic equipment, the challenge is, what is the challenge? The challenge is temperature control. But if you want to do the temperature control, you must understand the heat transfer. Whereas a heat transfer teacher would have told you that the basic idea of studying heat transfer is to understand the processes and be able to calculate the heat transfer. We go one step further in electronic cooling or whatever, in thermal control electronic equipment. You understand heat transfer. Please know the mechanisms of heat transfer. Please have ways and means of finding out how to calculate the heat transfer. Don't stop there. Put all of them in an equation like this and try to find out the temperature with the view that the goal is to, or the challenge is to be able to control the temperature. If you want to control the temperature, you have to know what is the equation which is governing the temperature. So if you want to know what is the equation governing the temperature, you have to go to the mother of all this, that is the thermodynamics. In that thermodynamics, first law of thermodynamics, find out which of the terms can be neglected. Then each of these terms, like internal energy and heat transfer, how do you model? Then comes the subject of thermodynamics, heat transfer and all this. And then now we will be in a position to pose the problem as how to control the temperature. So various strategies are available to control temperature. For simple things, you just leave it like that. Okay, if you leave your, if this is water is very cold, I took it from the cooler. If you leave it like this, because the room is hotter, after some time it will reach the temperature which I want, which is comfortable for me to drink. However, if you want to accelerate the process, I may put a fan, or just like coffee or tea, if you just leave it like that, it will cool at a certain rate. Otherwise, you've seen the local tea shop guy, how he does that. Basically, what he's doing is, he is an expert in heat transfer, right? So he does like this. So he increases the surface area, HA delta T is increased. So he's also very good in mechanics. He also understands the forces. That is why the coffee doesn't, or tea doesn't spill. He will do like this. Impossible. He will defy gravity. You know, local tea shop. Okay. He will do that. And he doesn't have any sensor. He doesn't have Navier-Stokes equation solver or COMSOL or fluent. He will know if he does twice, what will be the temperature. If he does thrice, what will be the temperature. So he will decide. If it is a small child, he will do many times. If it is an adult, he will do only once or twice. So basically, there is a heat transfer at work. There is also heat transfer because the tea shop boiler, there is so much of heat transfer which is taking place. So now coming back to electronic equipment, the whole idea of giving a very non-conventional introduction to this is now basically you must get the idea that the goal is not to find out Q. I mean Q supplied. Somebody will ask, "Sir, the heat transfer is known. If the heat transfer is known, P. Ramakrishnan, are you sleeping or you put the camera in that position? Hello? Hello? Hey, am I audible first?
Sir, it is audible, sir.
Ramakrishnan.
Yes, sir.
What
Audible.
happened? I got it.
Audible.
Is it audible or it's?
Audible, sir. It is audible.
It's audible or horrible?
Sir, audible.
Audible. Okay, audible. Okay. Say online. I say that online, all the teachers. How many of your teachers in this? Many of your teachers, right? Almost everybody.
Yes, sir.
Okay. Yeah. So many of your teachers. So the mantra now is, I am tired of saying this every day. No, am I audible? Am I audible? Am I audible? And no student will respond. No student will respond. Okay. So what happened? Last month in October, one of our deans took a class. Okay. He was doing online Google Meet, and his video was on and this thing, and he was using the campus internet. 9 to 9:50 was the class. 9:35 the internet went off. He didn't know that. He kept on talking. His PhD scholar is calling him some 8 missed call, 10 missed call. He is very busy teaching. Okay. So, and these fellows, nobody is saying anything. At 9:50 he stopped. Okay. Then he stopped the class, and the TA gave him the mobile numbers of students in the class. He called one fellow. He said, "Hey, what happened? How many minutes it was lost?" "No, sir, I logged in. I was not following the lecture." Second fellow said, "Sir, only 2 minutes were gone. So 15 minutes were gone." So this online class, the professors have become comedians. We are becoming comedians. Okay. So soon this online business has to end. All right.
Yes, sir. Yes,
Otherwise, we don't know what they are doing. See, many people, it is just it is videos. They will say, "Sir, bandwidth problem, sir," and video will be off. They will be muted. They will not give any response. So you don't know what is happening. All right. Anyway, I hope you are listening now. I don't know out of 42 are logged in. But how many people are there listening? I don't know. All right. So this is basically the framework. So based on this, people who are working in this can approach it from different viewpoints. Somebody can do only the heat sink design. Okay. Somebody can look only at the chip level. Somebody can look at the system level, or somebody can go to fundamental mechanisms and say that compared to forced convection cooling, I'll do jet impingement cooling. I will do liquid immersion cooling. Somebody will say I can add a nanofluid, right? And somebody will say that I use a phase change material, PCM based heat sink. Okay, so these are all going on. Okay, so this is the field. Okay, but now the basic problem in this device is, so suppose the Q supply versus time. Okay, if it is like this, what will happen? Or if it is like this, what will happen? Okay, or if it is like this, what will happen? Okay, Q versus time. So the problem gets more and more challenging. It gets more challenging because in a mobile device, it will be like this. So you will be running a lot of applications for 20 or 30 minutes. Many things will be, so you'll be attending an online class, it will get heated up, and then it will be switched off. So it will be not switched off. So there'll be only 1 or 2 apps running. So there is a cyclical heat duty, non-cyclical heat duty, or there could be something called power surge. So we should be in a position to handle all this. So for cooling of electronic equipment, thermal control, you must get some basic ideas in electrical engineering, and you should also find out what are the typical power levels involved in i7 processor, i8 processor, i5 7th generation, 8th generation, whatever. What are the typical power level generated by a server, by a supercomputer, by a cluster. Okay, what will be the typical heat load? What will be the typical heat load in a small data center or in an office space where there are 8 or 10 computers and so on. So it is not enough if you just know HA delta T epsilon sigma T to the power of 4 minus T to the power of 4 and so on. So you should have expertise in many subjects. Then there could be some multiple solutions. You should be able to combine and find out which solution is the best. So you have to understand the idea of optimization among various designs. What is the best design? So if you have to find out what the best design is, you must know what is best. So you must tell what is it that you are considering, for which you and you are seeking the best in that. For example, is it going to be the heat transfer? Is it going to be the pumping power? Or you want the cheapest? Or you want the best with minimum cost? So there could be one objective, multiple objectives, and so on. So this field will go on like this. So if you extend it further, there can be situations where there is an electronic equipment and you want to know the health. You want to know the health monitoring of this by measuring some parameters. For example, you can use ultrasonic rays and then send some ultrasonic waves to an aircraft. And the reflected waves will tell you the structural health of the aircraft, whether there are any hairline cracks. This is how they also do the health monitoring of aircraft. Okay, so this is one way of doing it. Or you can take a chemical plant or a chemical reactor or a nuclear reactor thermal power plant. You can remotely send some waves and non-destructive testing. So you can get the signature of the ultrasonic waves or infrared waves and find out whether there is a crack or some places there is a hot spot and so on. So if you are looking at all these temperatures, or if you're looking at these heat fluxes or what is emitted or what is coming out, what is reflected, and then you're doing some diagnostics on telling the health, what is the thermal health, what is the structural health of something, or what is the health of the human being based on a CT scan, based on a tomography or MRI scan and so on, you're typically solving what is called an inverse problem. So this, somebody is coughing, somebody is having fever, somebody's pulse oximetry is less than 95, all these are diagnostic of some disease. So the disease is the cause, whereas all these things are the fever, cold, cough, they are all the effects. So the job of a doctor is to correctly identify the cause of the causes. Much in the same way, in electronic equipment also, if you are looking at if continuously you are getting the temperature feed at various points in a data center, or if you're getting continuous feeds from the temperature across the various batteries in an electric vehicle, okay, so how will the air conditioner adjust, or how will the cooling system? So this is going to be a new field. Please note it down. Battery thermal management is going to be the big field in the next 10 to 15 years, when first from petrol cars we are moving to mild hybrid, then we're going to moderate hybrid, then we'll go to all electric. Okay, so it will happen over a period of next few decades. When that happens, these batteries will generate lot of heat. So whenever there is human enterprise, heat will be generated. So don't worry about that. But the prime mover may not be based on the first law of thermodynamics or second law of thermodynamics converting heat to work, but heat will be generated. Heat will be generated. Okay, so we'll have to remove the heat. There it's very critical, because the batteries are going to become bigger and bigger, because people want more comfort. People want all fancy cars which are coming in the market. They will be electrical avatars of this. So the batteries will become bigger and bigger. They'll generate more heat, and there'll be a lot of challenges. There'll be a lot of opportunities for thermal engineers to work there. The other possibility is the solar photovoltaic cell, where when it starts working, if the temperature is increased, the performance is going down. Therefore, research in solar, even in direct conversion of sunlight to electricity in this PV cell, there are opportunities available for thermal engineers to reduce the temperature in the backside using phase change material or something like that. So you can look up literature to find out 1 or 2 degrees drop, how much the efficiency will increase and so on. So these are some of the areas which will, of course, traditional areas like getting a better boiler and nuclear reactor cooling, nuclear reactor safety grade, decay heat removal system. When there is an accident, station blackout, what happens? So in all these very niche areas where not many engineers are required, but still a knowledge of heat transfer process required is many areas still exist. Now we have chosen a set of problems in our group. We work on a set of problems. basically not only as a part of academic training, we also try to get some problems from ISRO, IGCAR, and so on. And we try to solve some problems of interest to us. So in today's presentation, I will share some of the results with you of, okay, so now there is this, where am I now?
Present now is
No, I'm in which browser now? Huh?
press escape button.
Okay, I got back. Now present now.
Yes,
See,
sir.
I, for some reason, I'm a big fan of Zoom. Huh? Okay, so I'm not comfortable with this Gmeet. Where is this now? Share.
Yes, sir.
Wow, what is it showing? What is it showing now? Nothing.
You are presenting to everyone, sir. That is correct, sir. Press on that and okay. Yeah. Now we are.
Is it coming?
Yes, sir. It is able to. It is coming, sir.
So from beginning, slideshow. Is it
Yes,
okay?
sir.
Am I audible?
Yes, sir.
Okay, I'm
Yes,
audible.
sir.
Okay. All right. Okay, Kondareddy,
Yes, sir.
please see that first slide. So my Sishya, this Rajesh, is there in the audience. Rajesh Akula. He studied in that RJ Yukut. Huh?
Yes, sir.
So
News
he's-
video campus.
So he's very, very loyal. So next to IIT emblem, he put that emblem. Huh?
Okay. Yes, sir.
Huh? So, okay. So he's also under quarantine now. Rajesh, are you there? Rajesh.
Yes, sir.
Okay. So you're awake now after the heavy food, you didn't sleep.
No, sir.
Okay. This is Rajesh's work. Rajesh Akula is, okay, this for people from Rajiv Gandhi University of, what is it, Knowledge and?
Knowledge technologies.
Okay. So please be informed that Konda Reddy is now teaching there. Okay. So Murray Girish Kumar, my senior most PhD scholar, is basically from that place. Rajesh Akula is from that place. So I already have, any other student I have left out, Konda Reddy?
Baki Harish, sir.
Baki Hari. So there are 3 students, okay, in with one professor in IIT Madras who are from this, who are from your college, and they are all very hardworking students. Okay. So
Okay.
I'm quite happy. So you'll be happy. So something good is happening. Somebody started this, so I think it's a good project. All right. Outline of the talk: why use heat sinks? So the first few slides I have used it in other places also, so we can go over this very fast. But for some people who don't have the background, this may be important. Why use heat sinks? Why use PCMs within heat sink? PCM is a phase change material. For example, wax is a simple example which you can understand. So other than wax, we also have other things like N-icosane, N-docosane, paraffin wax. There are many other. So I talked about the normal wax, the candle wax. Compared to that, you have paraffin wax, you have N-icosane, docosane, tetracosane. There are many. You can have organic, inorganic, eutectic mixtures as phase change materials. The idea of a phase change material is that it will melt and it will solidify depending on whether you're putting heat or sending or pulling away the heat. Therefore, phase change takes place. So latent heat. So they have high latent heat capacity, because of which the temperatures can be under the temperature increase in electronic equipment can be kept under check. So for the purposes of electronic cooling, PCM is a very good strategy. Instead of just sensible heat transfer by using fins, fins will do the job for some time. You can radiatively enhance for some time in for up to some power level. But beyond a certain power level, you will have to use some things like this. What are the performance measures of PCM based heat sinks? the importance of heat discharge time in PCM based heat sinks. And oh, please mute. So, how to handle power surges? I told you about some power surges. Suddenly, the usage increases with the help of. Suppose, how do you handle power surges using PCM-based heat sinks? The key results and takeaway. All right. Basically, the idea of a heat sink is to maintain a system at an equilibrium temperature. The heat to maintain the system at a temperature. But here we are talking specifically about equilibrium temperature. I told you the equilibrium temperature is the steady state temperature, where the heat input to the system has to be equal to the heat leaving the system. This happens only under steady state. Oftentimes, Q in is not equal to Q out. When Q in is not equal to Q out, the system will become crazy. There is a MCP dt by d tau, which is non-zero. If it is positive, temperature is going to increase. If it is negative, temperature will decrease. So, come to the next point, next bullet. Even so, that means, however, the operation of most of the electronic devices most of the time is highly transient. Transient means it is a function of time. Therefore, the steady state. What is a steady state temperature? Steady state temperature may not be reached in electronic equipment. It may go up and down because if your mobile phone is not under same use, a lot of WhatsApp message will come. If you keep on, or you may listen to some YouTube, you may listen to some song, you may switch on the radio, you may do something else. Correct? And you may be checking the email, so you may be gaming. So it is under its usage pattern. Depending on the usage pattern, the power level is going up and down. Sometimes you see that suddenly that when you keep it on the ear, no, it is hot. But all the time it is not hot. You may be wondering suddenly my phone is not working. Please look at the number of apps which are running in the background. So whenever it is exceeding too much, automatically its temperature will increase. Okay. So therefore, the original idea of calculating the steady state temperature, we are saying that that problem has to be relooked. Okay. That problem has to be relooked. The goal could be how long the device will sustain. Okay, can it sustain below this set point temperature for a long period of time? The set point temperature is your acceptable working temperature, maximum acceptable working temperature, which I indicated on the blackboard also. Okay, if you just look at a heat flux of 0.5 watts per centimeter square, air cooling is inefficient. That means less than 0.5 watts per centimeter square, air cooling is sufficient. Okay. The major motivation for heat transfer researchers to seek new method of cooling electronics using a heat sink is oftentimes the heat flux is far more than 0.5 watts per centimeter square. So, natural convection cooling may not be enough. Even air cooling may not be enough. What are heat sinks? Heat sinks are basically passive heat exchanger devices. That means there is a fin, extended surfaces, or phase change material. Basically, they facilitate the heat exchange elements, heat generating elements to dissipate heat by providing more heat transfer surface. Q equal to HA delta T. Hey, can you see the board also now? Can you see the board?
Yes, sir. Yes, sir.
Okay. Okay, very good. So basically, this Q equal to HA delta T. So now let's say this is fixed. So the goal is now to bring this down. This is the goal. Okay. So you either increase the A or you increase the H. Okay. If Q is fixed and this or this is increasing, then this will go down. So this is basically fins. Okay. This is also newer. So newer technologies, liquid immersion cooling, spray cooling, mist cooling, whatever. Some people are saying nanofluid will do it, and so on. So fins, so will increase the A. Now we want to use a new technology plus fin and plus PCM. So this is what we are attempting. Okay. So because the PCM itself is a newer technology, so if you combine all this, we can get a heat sink where the area is increased, and it is not just the area is increased in air cooling situation. You increase the area, you also increase the latent heat. So you're trying to attack the problem by working on both H and A, so that this combined product, if it increases, then the delta T will go down. The idea is to, so this is for the steady state part of the problem. Okay, so if you don't like this, then you just do this. Okay, so goal now will be so the goal is not T is less than T max for as much time as possible. For as much time as possible. Generally, heat sinks are based on sensible heating and the temperature keeps on increasing with time. That means if you just have fins, okay, it will withstand up to a certain extent. After that, again, the temperature will increase. Okay, so you can have air cooling, natural convection plus radiation, or you can have air cooling forced convection, just like your automobile radiator. Okay, or the fins you must have seen in your 100cc bikes. You're also seen the radiator in the cars. Immersion cooling with natural convection. Okay, so you can just put something. So if you see sometimes when in houses nighttime, the mother or the wife or the sister, they want to convert milk to, they want to curdle milk to make yogurt or curd. Nighttime when it is very hot, if you add some already existing curd in the house to hot milk, it will not do properly. If you add curd to a very cold milk also, it will not work properly. So there is a temperature control there. If the temperature is not under control, next day morning you will not get the curd properly. Now already, let's say you forgot, the lady of the house or the male of the house, depending on who is having the cooking duties. So I leave it open now, whoever it is. So it is already late at 9 o'clock, 9:30. You want to make the milk into curd. Milk first has to be boiled. Okay, boil, done. Now it is cooling under the fan. You keep on touching. No, you touch. Ah, it is hot, hot, hot. But sleep is coming, or some Netflix, some web series is coming, or movie is coming, or Surya's film is released on OTT or something, or Allu Arjun's film is released. I don't know, whatever. So you want to go there, but this job has to be done, because if it cools too much and you have not done the job, finished. That milk will be wasted. So what you do sometimes is you take a bigger beaker of water and put this milk, this beaker which has got the hot milk, into that can. Okay, and then top you put on the fan also. But now the heat transfer game has changed. Therefore, if you just go and watch that movie, you're finished, because it will cool very fast. But the idea is, once you do that, normally if it will take 30 minutes, now in 10 or 15 minutes, you touch it, it comes to a bare, it comes to about 38, 40, 42 degrees. That is the ideal temperature, around 40 degrees. The temperature will be such that it will be cold if you take it as coffee, right? So that is the temperature of the coffee is around 45, 48. You take, so it should be lower than that. So that is immersion cooling natural convection. Okay. So sometimes these mothers also will do that. They are making this lactogen or whatever, okay, for this child, or Cerelac. So then the child is crying. So, but this damn thing has to cool down. So what they will do, they'll take a bigger beaker of water, they'll put that milk bottle in that, and then see, they didn't study heat transfer, they didn't attend the workshop like this, but still common sense heat transfer is working. Okay, even if you see the elephant, right? The elephant is constantly doing this. These two ears are the fins for the elephant. It has got excellent. You imagine, we ourselves generate so much of heat. The elephant is so big, therefore its metabolism is high, so it is generating a lot of heat. And because it is very heavy, it is not running, it cannot move very fast. So the general HA delta T for it is very low. Therefore, to increase the HA delta T, it is trying to increase the H. How does it increase? It flaps. Okay. So from natural convection, the elephant is making forced convection. Therefore, cooling will take place. So, like these mechanisms are available for birds also. Okay, birds also, if they don't cool, because they're flapping their wings very fast. They're flapping their wings very fast. Lot of heat is generated. Their brains will get damaged. So God has given some mechanism even for birds for cooling and all that. So naturally, even suddenly if your fear becomes 104, the shivering is whatever God has given to you. Shivering basically HA delta T is increased. So therefore, suddenly the heat is generated at the same level. Metabolism is at the same level. But what happens is the fever itself is a protection against the germs because the body is raising its temperature to kill the germs which have invaded. This could be coronavirus or a bacteria or a normal virus. So, but once beyond a certain temperature, the brain cannot withstand more than 104 or 105. Therefore, the hypothalamus, brain, all this, some computer is working inside. So it says, okay, danger, danger, danger. Okay. Immediately, the shutdown mechanism starts, HA delta T, immediately shivering starts. That is why when you're having high fever, they say you should not cover yourself with a woolen blanket because it is against the principles of heat transfer. Basically, you have to take a wet towel, okay, and wipe so that latent heat of water and put a fan, water vaporizes. So compared to HA delta T, m dot HFG, where HFG is the latent heat of vaporization. The m dot HFG, if the water evaporates or near the armpits, grandmother will tell, take a towel and this thing and put it. Worst case, they may say, just go under water. Okay, the tap, open the water, this thing, and immediately you have to wipe so that you don't catch cold and then go rush to the doctor. So these are some of the, so even this grandma medicines, even whatever we do. So what I'm saying is, attending workshop and this thing and doing VHD and writing papers, just look around, see in how many different places, how many different examples this heat transfer is there. So for electrical people can also look at electrical this, but heat transfer is so natural, right? So you can see that even if you see the sea breeze, land breeze, that is heat transfer. The monsoon is heat transfer. The cyclone is basically heat and mass transfer. Okay, lot of heat and mass transfer from the ocean, it is coming and hitting us. Okay, so if you look at rain also, okay, so water becomes clouds, water vapor. That is evaporation. That is heat transfer. Then there is CFD, fluid dynamics. By wind, by monsoon, it is coming. Okay, then when it rises, then there is something called the saturation temperature. That is thermodynamics. Then once it reaches above thermodynamic saturation temperature, the water vapor becomes the water vapor becomes water. If it goes further, it becomes ice. Then it is transported by winds. Then it dumps. Okay, it dumps as water. So water from the ocean, it comes back as water in the form of rain. Again, when there is flooding through the rivers and the drainage passages and the canals, it again goes to the. So God is operating a very big heat transfer engine. God is operating a very big. The hydrological cycle is the biggest heat engine. We are thinking that Ramagundam 2,500 megawatt power plant. What they are doing gigawatts. What is happening in nature is not megawatts. It's all gigawatt. So if you see everywhere, there is fluid mechanics, heat transfer, mass transfer, and thermodynamics. Okay, so you look around. All right. Now phase change materials can be classified. You can classify based on they can be organic, they can be inorganic, they can be eutectic. This paraffin is wax based. They are all organic, and some metallics can also be used. And salt hydrate. Salt hydrate is also good PCM. Eutectic is basically eutectic mixture. No, that's what we say. Organic, inorganic. So many combinations are there. Okay. Now the question is, why use PCM? Okay. PCM is because it works on the principle of latent heat. Just like fever can be reduced by putting water and going under a fan, then evaporation will take away a lot of heat. So the breakthrough in electronic cooling came when phase change material based heat sinks that exploit high latent heat began to be used. So the funda of the PCM based heat sink is basically the latent heat, which happens at the melting temperature. Of course, there are some fundas there. So the melting won't happen at one temperature, the solidest temperature, liquidest temperature. There is a mushy zone. So if you have to model it using your COMSOL, fluent and all that, there is something called the enthalpy porosity formulation. So you have to be careful. So there are many. So if you want to get into numerical methods, it takes a lot of years of hard preparatory work, hard work to get into numerical methods and research on this. Now look at N-ecosign. This is easily available. Many of our students use the N-ecosign. I'm editor of a journal and I see many papers coming from many places, even from tier 2 institutions in India. So I think N-ecosign everybody is getting. Even I have seen a lot of universities and also from NITs and other places. N-ecosign should be you can easily import it. That's what I assume. So I have put point number 3. density, thermal conductivity, all that is okay. Let's look at point number 3. Latent heat, 240 kilojoule per kg, very, very high. But there is no free lunch in this world. Look at column 2, thermal conductivity, very bad, 0.2 for the solid, 0.15 for the liquid. Okay. So therefore, automatically you see that God, when He gives you one, He will take away some other thing. It's a zero-sum game. Okay. You cannot, if you want to keep looking at your cake, then you cannot eat it. If you eat the cake is no longer there. So it is like that. So you cannot have the cake and eat it too. Okay. So you should not say like Tamil comedy, I will buy 2 cakes, sir. One cake I will eat and one cake. That is not the funda. The funda is there is only one cake. So either you see it or you eat it. Like this, you get high latent heat, but pay the penalty thermal conductivity. So what we guys will do? Okay, HA delta T, A can be increased passive way. How do we increase passive way? Fins. So combine fins with PCM. That's what our group has been doing. Now this many people are following what we are doing, and now I see many papers in this field, and our papers are not only cited. There are many groups which are working on this. So it is not just for the purpose of writing papers. When so many people do so much work, suddenly some brilliant idea will come. Of course, we are not able to show like what these fellows say every day. They are saying that 3G, 4G, 5G, because this is a old field. That is why I now encourage all of you people to see how to use machine learning, big data, and thermal sciences. So how to make heat transfer truly interdisciplinary. See whether heat transfer can be used in biology, cancer biology, can be used in cancer detection, heat transfer in atmospheric sciences, heat transfer in metallurgy, right? So and also we should not miss out on artificial intelligence, machine learning, big data. So see how you can use a lot of when CFD solutions are being generated, or you're having a heat exchanger experiment, lot of data is generated. See how you can use the principles of deep learning, machine learning, and all this. Otherwise, they will say that these fellows are doing it to a 100-year-old subject. They're all old people. Same HA delta T, they are saying. They'll finish us off. Okay. Therefore, we have to bring all these into mainstream. Otherwise, heat transfer will die. Okay. So please have it at the. So whatever I have done, this thing you should not follow. Next 40 years, it will not be there. Okay. So you'll have to continuously innovate. Okay? Otherwise, society is cruel. You'll just fall by the wayside. Now, please tell me how many thermodynamics journals are there? How many people are doing research in thermodynamics? Thermodynamics is well understood. Or also, is anybody doing research on electrical motor or electrical generator? Some little bit is there, no brushless, all that, but that's all very little. Otherwise, it's considered to be very mature. Who is doing research on electrical transformer? Okay. So, and they are threatening, no, they will stop the diesel engine and all that. So, we have to be, so basically, we should be strong in fundamentals. We should like certain fields, but we should see how the world is changing, and we should be able to quickly adapt. Otherwise, we'll be left out. They will say that this fellow is doing old things, he's only doing recycling the same thing. That's what all people are saying. No, heat transfer people are stuck with something called heat transfer coefficient H. This was defined 100 years back. They are not able to come out of this H. Okay, HA delta T. So please say something else. Why are you always saying HA delta T? But that thing is the most important for us. We are able to design many things. Okay. But that is not enough, it seems. So we'll have to change sooner than later. Okay. So the charging cycle is the heat is coming from the bottom. I explained it on the blackboard. Adiabatic wall means so the heat is transferred only from the top. Discharging means the heating is stopped and it cools. So charging is when the PCM is melting. The discharging is from the melting, it is again resolidifies. Okay. Now, please look at the typical temperature time history. This is called the temperature time history. A is the starting point. A, B, C, D is heating. D, E, F, G is the cooling. Okay. But you can see that B to C is where the latent heat absorption takes place. But since it happens over a temperature difference, small temperature difference, it is not showing much. That is TC minus TB is not much. That is the solidus and liquidus temperature. So D is the maximum temperature, and from D, the power is switched off. D to E is sensible cooling. E to F again is the latent heat rejection, and FG is the sensible cooling. This is a typical temperature time history of consisting of both the charging and discharging cycle. This can also represent the life cycle of a typical one full cycle of a electronic equipment or whatever, right? So charging plus discharging. Heat is added, and it is also stopped and it is cooled. So therefore, the metric for a PCM-based heatsink would be what are the performance measures, latent heat time. So the point B to C, the point B to point C has to be stretched or maximized. Okay. Furthermore, the solidification time must be as small as possible. That means E to F must be reduced, B to C must be increased, but E to F must be decreased. But this is impossible. I don't want to work hard, but I want high salary. I don't want to study, but I want to get maximum marks in the exam. How is it possible? Therefore, if BC has to be stretched, EF will also be stretched. Therefore, you have to do some interventions. That means you will have to come out with some jugaad, or you have to come out with some improvements. You have to come with some innovation. You have to come out with some creative solution to attack this twin problem of stretching B to C and contracting E to F. Naturally, they will not happen simultaneously. In a heat exchanger, if you want to increase the heat transfer, okay, buy one, get one free. They say, no, if you want to increase the heat transfer, pressure drop will increase. But pressure drop is undesirable, whereas high heat transfer is desirable. But there is no solution in the world where you will get all desirable things. Even in life, it is not possible. Even with some other person in a relationship, also there will be something about some other person whom you don't like. But if you think deeply, there will also be something which you will like. Therefore, there's no thing of perfect. Perfection can be a disease also, right? So, therefore, what you have to do is a pragmatic, practical approach would be try to stretch B to C as much as possible. Try to reduce EF as much as possible. This as much as possible is an endeavor, is an activity. It can take 10 or 15 years. You may be a professor guiding so many students. So at the end of 10 or 15 years, how much did you stretch B to C? How much did you reduce E to F? This will be your contribution. Like that, you can choose your field. It could be in electrical engineering, mechanical engineering, whatever, or it could be in data science. Okay. So you have to settle down to a line of investigation and you have to go deep. And for many years, you have to work. Only then some pearls and diamonds and gold will come out. Otherwise, simply seeing what other people are doing and this thing is fine for the initial years. After some time, you have to settle down to a line of investigation. By 35, 40 years, you have to settle down. Then about 15, 20 years, you have to settle down. After that, anyway, your energy, you will become age, 60 years, you will anyway, all the energy will go down and life will catch up. Okay. So this is I'm talking about the charging and discharging cycle of a researcher. Okay. I'm talking about charging and discharging cycle of a researcher's life. That is also A, B, C, D, E, F, G only. Okay. The D is the peak. The peak you have to hit at the age of 40 to 45, you have to hit the peak. Then because of your biological disease, you will reach F or G. For example, I'm already 50 plus. So I will also reach F or G and one day we will also reach. But I won't tell you now where I am in this, what is my current position. All right. But don't think that you can stay at D for a long time. Okay. So try to stretch the time of operation so that from D onwards, you have to go down. Okay. Try to stretch A to D in your life also. So don't try to do always easy things. Try to do difficult things. Okay. Become a better human being. Okay. All right. So reducing the discharge time is one of the key criteria in the design of a PCM-based heatsink. For intermittent operation, I told you on, off, on, off, on, off. They are most likely to be encountered in practice. Reduction in discharge time is as important as that of the improvement in charging time. Therefore, Rajesh Akula did his work where we said that we'll put some horizontal baffles. Okay, they are some made of some conducting material. So wherein we stop the convection or there's an intervention which disrupts the melting mechanism and the convection inside in the heat sink, so that we will see whether this outcome is improved. Okay, so this is the heat sink which is fabricated in the heat transfer lab, and we have got facilities to do experiments. Okay, data logger, this thing, all right. So calibration units, this thing, computers, all this. Okay, so you can see that some thermocouples are there. It is heating from the bottom. So please look at this. So there is a baffle. Okay, so the baffle is like this. Let's say if this is one surface, this is one baffle, and this is another baffle. They are placed at different heights, and you can see it's some sort of a semi-obstruction. It's not a full obstruction, it is a semi-obstruction. Now, the whole idea now is to study the performance, charging and discharging for a heat sink with baffle and a heat sink without baffle. Therefore, it stands to reason, first you have to make two heat sinks, one with the baffle and one without the baffle. Then once you have that, then you can do further experiments. You can pour the ecozine or wax, you need not pour. So with baffle, with PCM, with baffle, no PCM, no baffle, no PCM. So you can have multiple combinations. Then you study it scientifically, do repeatability test, do the uncertainty analysis, find out what are the uncertainties and errors in the measurement. No cheating, report it properly. If you are not getting, find out where there is a thermocouple is not working properly, something is leaking, it is not heating, fix all the problems. Get scientifically reliable data, process it properly, discuss with your professor. Some interesting science will come out. If something is interesting, try to publish. This is the charging and discharging cycle for a research article or a research investigation. Please note everything as a cycle. Okay, baffle, yes. Okay, so Rajesh's work is like this. So the top is acrylic has been given. So he has also put a mechanism where we can change the orientation of the heat sink. Because often in real life, it need not be only horizontal or vertical heat sink. It could be placed in other positions. Okay, so this study focuses on two types of heat sinks: heat sink without baffle and heat sink with baffle. The PCM fill ratios are, if this is the water bottle, this is the heat sink. So water bottle, 33% water, that is the first case. 66% water, second case. 99% is full bottle. Instead of water, we are adding the PCM. Heat sink orientation, 0, 45. Rajesh, which is 0, horizontal or vertical? Rajesh,
Sir,
horizontal or vertical? Which is
when
0?
the walls are vertical, then it is 0, sir.
That
Walls
is
are
okay. What walls are vertical? Which wall? You're answering like IIT student, man. Huh? This. Okay, so the walls are vertical, it is 0. All right. Now, 66% fill ratio, you can see that it's not a great result. Okay. So when a student comes and tells me, I'll tell him that, okay, there is no need to add baffle because baffle means going to the workshop and putting more money, more effort. Now it seems that 66% no use. So there is one set of plots. Look at the left hand side, without baffle, with baffle, charging and discharging. We can't see much difference. Okay. Except that with baffle, you got a slightly enhanced charging time, right? Okay. So with baffles, you got a slightly enhanced charge, which is good for a 180 degrees orientation. So across orientations, the experiment is for across orientation with and without baffles. So for a 66% fill ratio, so you can see these are the control variables. What are the control variables? Fill ratio, with and without baffle, and orientation. Okay. Now, so this is the cycle of temperature for the 99% fill ratio. That means heat sink is almost filled. Now, the standout result is the blue. The blue. Look at the blue. Blue is the discharge cycle from compared to green and red, it came down. Therefore, I'm having a much shorter discharge time if I have a heater with baffle. Look at the legend of the figure. Left hand side within the text box, you have put 99% fill ratio. Right hand side, red, heat transfer without baffle. Blue, heater with baffle. Very good. So, okay, very good. The discharging cycle is reduced. What about the charging cycle? Not badly off. It is also doing reasonably well. Therefore, 99% fill ratio, 0 orientation, and that heat load could be anything. So somehow we are trying to see that we are able to see that this is doing fairly well. This is very good news. Okay. So now we are trying to explain what is happening. So there is something, the latent heat rejection takes place between C and D. So whatever C and D, and then the subsequent cooling, and look at the view graph on the left hand side. And D dash to E is where the sensible cooling is taking place. So you can see that the sensible cooling, it is sharp. The temperature gradient is sharp. Okay. Quick latent heat rejection during phase change and rapid sensible cooling. These are responsible for this improved performance. This is after getting the results, we are digging deeper into it and trying to investigate the scientific causes for why it is happening. So now this is apart from the experiments. So we have also done supporting numerical calculations with the CFD. computational fluid dynamics using ANSYS Fluent. So what we do what is called matchup. What is this matchup? We are assuming adiabatic conditions. The adiabatic conditions won't exist in practice. So what we do is we run the simulations with different heat loss coefficients from the side and the top, and then tune the model such that for one case we get the closest agreement. And whatever heat loss coefficient is there, we use it for running subsequent calculations. Now these colors are liquid fraction and temperatures. We cannot get so much of detail with just thermocouple measurements. So it is a good idea to combine experiments and simulations so that detailed physics, additional insights, that and your answers to the question of why with a baffle it is better, these can be answered more confidently, more clearly if you're having supporting calculations which are well validated. Now look at this. Bottom is with baffle and top is without baffle. So you can see the melt front, how it approaches. Right hand side is the temperature. You can see these baffles. There is a cool green. Right hand side, there is a cool green region in between the two baffles. So it is not fully red as opposed to the top. Fully red is high temperature. Therefore, there's a cool region. Therefore, it is helping us. Okay. Okay. So this is conclusions for part 1. So among all orientations, 0 degree is the best. Baffles are very effective in decreasing the discharge times. Baffles introduce cold spots. This is the finding. This finding, for example, the bullet number 3 is not possible even if you do very carefully controlled experiment, unless you put many thermocouples in the core region, which will disturb your experiments. Also, it is very difficult to do that experimentally. Okay. So the last point is the baffles are very effective in dealing with transient heat loads. Okay. All right. So power surges are very important because power surge is suddenly there will be a baseline power is 10 watts. Suddenly it becomes 20 watts. Or you can see in the evening time, so there is a 5 megawatts power or 50 megawatts in the city. Suddenly it becomes 65 megawatts. You get a voltage drop. Suddenly the power will trip. Okay. So the power surge is very frequent. It occurs in electrical engineering. It also occurs in electronics. Okay. So examples are electromechanical actuators in aircraft, ultra capacitor power electric buses, and then whatever is used in automated external defibrillators. This is kept in hospital. Somebody has a cardiac arrest. We put this, no? So they'll give that electric shock to revive him. Lack of effective cooling to deal with this can lead to rapid increase in the temperature. Okay. So even if you have got a welding joint, if you have a power surge, and if this power surge is not controlled, power surge is not, see, funda is, power surge is not under your control. But the response to the power surge is the job. The response to the power surge is under the control of the thermal engineer. Whatever is a power surge, we should be able to absorb the shock. We are like the thermal shock absorber. We are like the shock absorber for car. So this is the thermal design. This is the thermal design. This is the control of electronic equipment. So within limits, whatever surge is taking place, you should be able to absorb. It should not rapidly increase the temperature or cause violent fluctuations in the temperature, which is not good for the health of the equipment. Okay, that's what is written. Finally, this results in both thermal and mechanical failure of the devices. Okay, so now what Rajesh did was he considered heat sink. TC is thermal conductivity enhancer, that is fin or baffle. Then he considered 2 types of baffles, that is configuration B for Bombay and configuration D for Delhi. The C for Calcutta on the right side is basically the fin configuration. For all these things, we considered a spike. We will tell you how the spike is. One is, you can see that heat flux 1, bottom, first row, 10 watts continuously for 3000 seconds. Total energy is 3000 joule. Now all this masala we are doing, the total energy will be the same. Heat input 2 is 20 for 300 seconds, 0 for 100 seconds, 20, 20, 0, 20, 0, 20, 0. Heat input 3 is 10, 20, 10, 20, 10, 20. So heat input 4 is, okay, 10, 100 and 50. Okay, that is the super of all that. So that heat flux 4, you can see that top view graph. So the 2 triangles high. So that is a very high power surge. Now you have to see which of these configurations is, which of these 4 configurations is handling it better. Do experiments, do simulation, do matchup, Look at the plots very carefully, infer the signs and do some signs. All right. Okay. Now you can see that baffles of without thermal conductivity enhancer is the highest. Blue is the highest. Temperature is increasing like anything. So it is out of control. Blue is out of control. So red is good. Okay. Red is good. Green is good. And black is also reasonably good. So this is basically for the charging cycle. Now look at this, up and down, up down, up down, up down. This is the base temperature for this cyclic heat load 2, up down, because this is first one is heat input 1. What is heat input 1? Uniform. Okay. Up down, up down, up down. Now you can see the difference. The melt fraction, the red line, right side, the melt fraction is very good for vertical fins. Okay. So the heat sink with vertical fins, because the melt fraction is high, there's a lot of melting which is taking place. When it melts, it's like a shock absorber. It takes so much of heat. It ensures that it melts so that the temperature does not go up. Okay. However, during all the discharge cycles with baffles, the blue is very good. Okay. So that is the whole thing. All right. So now this is some additional supporting evidence. This is evidence based on calculations. So you can see how the you can see this. Please look at what the contours are. Okay, 0 to 1 means it's a liquid fraction. So baffles of type 1 and baffles of type 2, you can see that melting of type 1 is you can see the red, more red here. Right hand side you can see red there. Okay, you can see for yourself. So baffles of type 1 and 2, so I have almost the same temperature till 1600 seconds. After that, heat sink with baffles of type 1 outperforms. So type 1 more red color. So good news for us, it outperforms. Okay. Now heat input 3. So in the interest of time, I'll quickly go through. So you can see that the temperature drop during discharge cycle is basically 5.9 degrees for 1400 to 1800 seconds. What is that 700 to 1100, 1400 to 1800? It's basically where the power surge is taking place. So what we have calculated is how much is the temperature drop in the discharge cycle. You can see that it is going up and down. No, whenever it is going down, that is a temperature drop. So you can see that the baffles have a clear advantage. Okay. Conclusions for part 2: PCM based heat sinks hold promise for high heat flux applications in on-off mode. Pins are effective in the charging cycle, but baffles significantly enhance temperature drop during the discharge cycle. Okay. What is the takeaway? So baffle is one area we can pursue. Then baffle with fin will improve both the charging and the discharge. This is how you go deep. I'm not see what I'm telling you today is like a siddhant, it is a philosophy. How you go about the research problem. So in real life, this 5 watts, this 200 seconds, 100 seconds may not be important, but the academic, but it's just not an academic exercise. There is a method, there is a way by which systematically we go about finding out the reasons for the performance or underperformance and how to improve. Okay, so this is so we can also do multi-objective optimization. We can do many things. Okay, so this is a recent paper by Rajesh in International Journal of Thermal Sciences. He has done some other work also, but that is not part of this. Okay, so we will continue our work and we'll combine baffles with fins, and then we'll look at it for power surges and cyclic heat loads and so on. So I will stop the sharing now. Stop presenting. So I'm back.
Sir,
All right.
we take
I'll
questions.
take questions now. Yeah, thank you very much. So you can go on. The takeaway is, needless to say, electronic equipment cooling is a challenging problem. So in several fields, so this is going to be important for at least another 15-20 years. So you can choose whichever problem you want to work on, depending on your facilities, and okay, and then try to link up with the industries and try to solve some practical problems. Okay.
Thank you, sir.
Thank you very much. How many people are there? Oh.
41 are there, sir. If any questions you have from participants, you can ask. Seems so no questions. So thank you, sir, for your excellent presentation on challenges in electronic cooling. And,
all right.
we remembered 10 years back your classes when we are sitting in the classroom.
Hmm.
I am very thankful to you, sir. And,
Yeah. Okay. Pleasure. So good luck to all of you. Do well. So shall I take leave?
Okay, sir. Okay, sir.
Okay. Thank you.
Right. Participants, I shared feedback form in the chat box just to submit for taking the attendance as well as for giving participation certificate. And I thank Dr. Gnanasekaran and Dr. Tapan, who are the students of Professor C. Balaji, who are attended for this session.
Thank you, Dr. Kondareddy, for this opportunity.
Thank you.
Yeah.
Right.